So yeah, today I'm gonna discuss additive manufacturing on the moon from Lunar soil, as called regolith. So it's a huge part of my thesis work, which is being a collaboration between two French labs, which are the ICA for all the material science concerns and IRAP for all the planetology aspects, of course. And so I will first have to introduce you my working material, which is an analog we are developing in both labs. Then I will show you some details about the process I'm using, which is a selective laser melting, which will allows me to talk about the relationship between the process and the material and all the relevant physical properties. And then finally, I will present you our additive manufacturing samples and their mechanical behavior. So you're not gonna learn anything about the lunar regolith in itself, but what I want to insist on today is that, of course, regolith has a huge range of chemical compositions, and two main aspects I will insist on today is the fact that with space weathering and all the formation mechanism of the moon, you have a lot of irregular and acicular particles, and a lot of amorphous phases, which are commonly called glass. And that will have a huge aspect on all the properties of the material we are going to make at the end. And so a few decades ago, my PhD supervisors found a place in France, which is called the Pic d'Isson, which provides us a basaltic material that is quite close to what we could find on the Marais regions, with a quite low content of titanium, as you can see on the chemical composition on the bottom of the slide. And so a huge aspect about this analog is the fact that the original basalt in itself is 100% crystalline. So what we can do is melt it, quench it, and crush it to have this glass powder. And so just by mixing the original basaltic powder with glass powder, we can really control precisely the amount of glass material we have in the analog. So now about the process I'm using. The concept is quite simple. You have a powder layer that is being exposed by a laser source. And so you're gonna melt the powder and gonna draw the shape of the object. And so you just have to add your layers of powder one by one to actually manufacture your object in 3D. And so the aspect that interests me here is the quantity of energy I'm bringing to the material, which is called the volumetric energy density. Because if I don't bring enough energy, I will create some lack of fusions and so porosities. And that's the opposite. If I bring too much energy to the material, I will vaporize some content and I will also create some porosities. And that's not a good thing for the mechanical properties. So why using this method more than another? It's because of two main reasons. There's no need for an organic binder and no post-treatment neither, like debinding or sintering. And so that's a lot of payload you can save for other experiments during your lunar missions. So now we want to understand how the process in itself interact with the powder. And so the first question we have to ask ourselves is how much of the quantity of energy I'm bringing with the laser is actually absorbed by the powder. And so that's all about the optical properties that you are familiar about with all the absorptivity. And then for higher temperatures above 1000 degrees, all the emissivity aspects. Then you want to know how quick and how far the heat you are creating will be conducted in this granular media. And then, of course, finally, you want also to know at which point your material is actually going to melt and what kind of crystalline structure you can get at the end of the process. And for all those properties, there is a huge impact of the proportion of glass you have at the beginning. For example, starting with optical properties, what you have here is the reflectance of our analog depending on its glass concentration. And so I'm not gonna discuss like the behavior, the aspects of the curves, but if you stick to the SLM laser wavelength, you can see that just going from the 100% basaltic powder to completely glassy content, you are dropping from 8% of reflectance to 4% of reflectance. So in itself, it's already a good properties for us because, of course, the more the powder will absorb the light, and the less you have to spend some energy to bring some power to the laser. We have also conducted some differential scanning calorimetry. So for those who are not familiar with this technique, the point is to have a sample on which we apply a temperature program. So here we are heating until 1,500 degrees Celsius and then going back cooling. And so what we monitor is a heat flow going in or out of the sample, because every time you have a transformation of phase, it will be either an exothermic or endothermic. So for example, if you take the original basalt powder, when you heat, you have a huge melting area, and then you have the corresponding crystallization area cooling down. And so in the same way, if you take a look at the glass powder, you have two phenomena appearing. First, the glass transition temperature, which is the point at which glass is entering into a viscous state, it's gaining some mobility. And after that, you have the annealing area, in which glass has enough energy to actually recrystallize into a new phase. And so this annealing area is endothermic, so it could help us to reduce a little bit the energy of the process. And it gives us a precious information about the kind of material we can get at the end of the SLM process. So finally, I can show you some SLM samples and some microstructure. So what you have here are two samples in the same operating conditions with the same energies, the same laser parameters. But on the left, what you have is a 100% crystalline powders, which has been used to make those samples. And so what you can see on the micrographs here is that the cylinders we have made are quite with a lot of porosities and irregular shape. So we have on those samples an average porosity of 14%. And so just by changing one condition, it's the proportion of amorphous powder we have. So we have made a mix between 50% basaltic powder and 50% glass, because we want to have some reasonable content of glass and not having 100% glass content, which would be weird on the moon. You can see that the microstructure is generally quite better and more regular, with a lot less porosities, because we are dropping to 4% of porosity. So that confirms that just the fact of adding some glass material in the analog is actually improving a lot the microstructure at the end. Probably we don't have the exact reason yet, but probably because of the mobility it's bringing, as I was saying, and all the physical properties like optical properties, it is actually changing. So now I will show you some aspects about the mechanical behavior, because we have conducted some compression strength tests. So the obvious thing here is about like the maximum stress we can apply to our cylinders. So we have quite promising values with a compressive strength of 56 megapascal at max. But the reason why we have those values are because you can see on the end of the curves, it's slightly non-linear before the failure. So that's a sign of progressive multi-cracking in the material. And so that can be explained because at the end of the process, we still have some crystalline inclusions in the material that are actually acting like crack deflectors. So it's a good thing to have at the end of the process still some residual crystalline phase in the material that can be acting to deflect those cracks at the end. So what's up next? We want to tune to the lunar regolith high variability, for example, by adding some titanium-rich phases like ilmenite to have the aspect of the variation of composition. Then we want also to find some ways to increase the mechanical properties. For example, by adding some metallic powders that could be used from isru techniques. And so to have a composite material that could be more ductile. And then, of course, we need to think about objects with an identified purpose for future lunar space programs. I'm thinking about Artemis, of course, but could be anything. So that's all for me. Thank you for your attention.